Just checking. Okay, so we're recording this one. Now, if you go to your Zoom, okay, welcome all. This is a full seminar series for CNRE, the Center for Naval Research and Education. I'm Mahesh. I've been working faculty in Navy and director of the center. And this is our inaugural seminar for the center. And those of you who don't know, our goal is to basically perform research into pressing S&T problems of naval interest. And the seminar is an important part of an activity, so that it's a place to bring together multidisciplinary problems. And so I'm very happy that our first speaker, inaugural speaker, is Professor Dave Dowling. As you know, he is chair and previous professor of marine and offshore design performance in Navy. He's also faculty in the mechanical engineering department. And Dave has been at the University of Michigan since 1992. In addition to his impressive record, he's a leader in the field of fluid mechanics and acoustics. And in addition to his impressive publication record, he's the primary author of a very influential textbook in fluid mechanics that's used typically at the senior, the first year graduate level. He's a fellow of important associations and societies. And in addition to some records, he's received awards for teaching as well. I won't list them all, but just mention one such award, that being the ASME Rural Gold Medal for noise control and acoustics for his work in that area. Right. So thank you again. And take it.
No, thank you. So first thing, similar to work best, we ask questions as they occur. So I'm expecting to be interrupted, so please go forward with that. Okay, this talk was a hot issue 20 years ago. However, things that involve Navy research typically come back around. So some of the hardware I'm going to show you today is actually back in service, although it's being used this time for cavitation tests, whereas this was entirely single-phase flow. Okay, based on the amount of stuff we did and where we did it, there's a bunch of people have to be recognized. The whole crew at Card Rock helped out with the design of the foil and also the mounting structure. Some of the main people to pick out there, okay, Bill Blake and Ted Farabee and John Dershfeld pretty much essentially helped set up the shape of the foil. And from the University of Michigan, we had a number of people also contributed. Josh Hamill and Carolyn Judge were involved. And I should mention this. Dwayne Burgoyne was the main PhD student, and my colleague Steve Cessio, and I were the sort of co-faculty leads on this. I think these people are all retired now from LAR, but they were very good contract monitors. Liked them a lot. Okay, so this is the outline, background, motivation, the setup. And this is hopefully the interesting stuff here with the experimental results and then summary and conclusions. So background and motivation. So I was asked specifically to start at a very foundational level. So if you grab the Navier-Stokes equations, and you throw away all the terms that are annoying, you can then fuss with what's left, and you can make the acoustic wave equation. So acoustics, it's the linear theory of fluid dynamics, the same way that vibrations is the linear theory of dynamics. And acoustic waves provide the primary means for remote sensing in the ocean. So almost everything we know about the interior of the ocean comes from our ability to send and receive acoustic waves. And these bathymetry maps first came out in the 60s and 70s, all based on sound waves. There's no way that you took a bunch of divers and went down there and took pictures of the bottom. This all came from sound waves. And as you might be aware, there's a large fraction of the global GDP that depends on the extraction of resources from inside the Earth's crust. And acoustics is used both on land and in the ocean to find places where these things reside. So then, now switching to the more specific problem. So navies the world over use sonar underwater the same way that you're probably used to using radar above. And that you try to find things, you want to monitor things, you want to track things. For the Navy, there's two priorities for acoustic underwater. The first thing, you think of yourself as, let's say, the captain of the surface ship. You might deploy, might dip an array, might tow an array, and you're looking for something. You're hunting for your adversary. The other thing is you might be in the device that's trying to remain hidden. So that application requires this thing to make a little noise. And it's sort of interesting. This is one big difference between sonar and radar. If you've got something moving in the water that's unavoidable, you're going to make some noise. Whereas you can fly an aircraft through the air and it doesn't automatically make radio waves. So it turns out there's both active and passive sonar, but a lot of the applications, particularly in the hunting and hiding stuff, is all passive. So the talk today is it's motivated by the remain undetected part. So remain undetected, the flow oscillations that produce acoustic waves have to be suppressed. And that's where the vortex shedding stuff comes in. If you could somehow get the submarine to go forward at a steady speed, the propeller turn at a relatively steady rate, you'd still get the blade rate from the propeller, but you wouldn't get the tonal vortex shedding, which is the signature that people look for. So the phenomenon of interest here is vortex shedding. Now the top picture you can see is just of a regular circular cylinder, and you can see that it produces an oscillating wake structure which has a Struhal number. Now, I think we'd all agree that this is a blunt trailing edge. Now, there's a big difference between an aircraft wing that you see at the airport and a Navy propeller blade. The big thing is the aircraft never have to fly backwards. However, there's somewhere forward of this inside the ship, there's enough torque, horsepower, and metal that even at full speed ahead, you can turn the propeller backwards. And if this thing came way out here, that gorgeous tapered trailing edge that you see on aircraft, you bend it when you run it backwards. And then it doesn't work going forward or backward very well. So the Navy winds up with blunted trailing edges. That means that you would then typically wind up shedding some vorticity from the lower surface and from the upper surface. And those two shear layers are separated by a large enough distance so that you wind up with some of the effects of bluntness. And that's what you don't want, but you kind of have to have it because the ship's also got to operate. So the off-design conditions, sometimes called crashback, lead to the blunted trailing edge. So you can consider vortex shedding while thinking about the size of the ship, size of the propeller. If you turn the propeller forward, you might go at a number of speeds. So the typical flow speeds of interest sort of 2 to 20 meters a second. Typical chord length, sort of 2 to 4 meters when you go back. Oops, this way. This nominal near wake width is typically about 1% of the chord. If I take those numbers and do scaling, I get to 10 to 200 hertz. Now, what's the problem here? It's the tonal noise. So if I plotted, let's say this is pressure fluctuation spectrum versus frequency. This broadband stuff is a lot of the whooshing, wave breaking, air rushing over the surface, bubbles coming to the surface kind of sounds like shh. So if you could make only that sound, you'd be okay, because then you'd sound like the rest of the environment. This is the trombone. Okay? So if your device makes the trombone sound, there's nothing in the ocean that does that naturally. Okay? So why would this occur? Well, it turns out that if I take a hydrofoil, now there's a plan for view, so you're looking down on this, okay? And then if you had, this is a cartoon, if you had an instantaneous cut of the surface pressure fluctuation, it would be potentially some random pattern. And if, as the flow leaves the trailing edge, it leaves at all different speeds, at all slightly different angles of attack, it'll then make a bundle of vortex lines, which don't necessarily have any structure. That stuff, where it's all random, can produce this. And that's okay. However, if you wind up with a condition where it's all uniform and you're essentially sending off vortices, overturning, underturning, overturning, underturning, you wind up, and you can think about this from a potential flow point of view, they put a vortex here in that direction. It puts positive pressure on the top and suction pressure on the bottom. Then if the next one comes off and goes the other way, then I get the signs to flip. The trailing edge means a giant dipole noise. Okay? And that's what radiates sound. So because of the structure of the near wave, you can wind up with this thing. And then, as the Navy's learned over the years, propeller, or the bow planes, or the sailplanes, whatever it is that's doing the vortex shedding, those also have mechanical resonances. So if the vortex shedding matches the mechanical resonance, it's called singing. Now it's like the whole ocean basin will hear you. So the idea here is to try to figure out, okay, what's going to lead from the hiding standpoint to the absence of the tonal peak and the absence of the structural vortex shedding. And the hope at the time, that was a while ago, is can this be predicted with computations? Yes?
What's FK in this case, the tonal frequency?
This is the frequency of the vortex shedding.
So what's the value?
What?
What's the value you heard?
They're typically in 10 to 200.
Okay, how does it compare to like the natural sing of whales communicating?
Okay, it's in approximately the same range. However, the whale songs are relatively short compared to the transit time for a submarine to go across an ocean basin. So while they'll get this nice squeaky, loud noise that ends after 10 seconds, okay, the submarine doesn't go for 10 seconds, stop and start again. It just keeps going. So you wind up with really clean tonals because of the nominal steady state operation. So, good question. All right, so the motivation for the experiments we did, we wanted to provide high Reynolds number archival data. Even 20 years ago, they were working on computational models for this. Also to improve the scaling laws through the empirical methods. And then, if possible, and because it's a 6-1 project, extend the fundamental understanding. So the basic thing we're going to be looking at then is a 2-dimensional hydrofoil with a cross-section that looks something like that. The chord length and the important scaling parameter. So if I want to go to high Reynolds number, I'm primarily going to be having high flow speed and a large chord. I'm going to make it realistic. The shape that was chosen was actually sort of generic for a Navy propeller blade. So if you take one of these things, have anybody seen one of these up close? This is not from a submarine, but it's just this giant brass potato chip. But if you cut it at essentially a constant radius, you'll get a shape that looks approximately like that. Now, if this was an academic hydrofoil, the bottom surface was perfectly flat, so we had a very, 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 very clean, very well-defined surface from which to define angle of attack. The actual ones have a little curvature on both sides. And then you can see the trailing edge was a little bit blunted. So a lot of prior work in this area, and all came in with Reynolds numbers of about 2 million. Our experiments sort of start there and then went to 50 million, which is about the same as the root chord Reynolds number on a 747 during takeoff or landing. So this is serious stuff. Real size, real speeds, real forces. So experimental setup. So here's the actual specification of the model. So as you can see, it's a modified NACA 16. The symmetric NACA 16 you might be used to seeing is a circular arc on the top and a circular arc on the bottom. This gives you a pressure coefficient, goes up, runs flat, comes back down, and that's the best for preventing cavitation. So the chord length, it actually was 7 feet. But to make it modern, we went to metric. So the 2.134 meters, that's 7 feet. The span is 10 feet because that fit in the test facility. The material, this was actually fabricated by Bird Johnson Company, which was making propeller blades for the Navy at the time. So it's actually made out of Navy stuff. It's solid nickel, aluminum, bronze. and put it in the water, take it out of the water, put it in the water, take it out of the water. Just got to scrape the barnacles off, otherwise it's perfect, never rusts. It started as a casting with 16,000 pounds, 2,000 pounds of chips later. It was the foil. I'll show you in the next picture. Now, the interesting part for the talk. We tested two trailing edges. The first one is cleverly called baseline, and it's not quite as thickened. The second one, called modified, involved adding a strip of metals, probably only about 15 pounds. Essentially stuck it on the back, and that blunted the trailing edge a little more. The more slender trailing edge was not in favor by the Navy. The blunter one was. Okay? It turns out by making it blunting, you can make the whole foil a little shorter, but you can still have the thickness you want, and you can generate more lift without having to have the foil be quite as big. So from a performance standpoint, the powering people said, yeah, we want the thick trailing edge. The acoustics people, no, we don't. So this was the test setup. So for the rest of the talk, we'll be seeing baseline and modified from time to time. Here's the actual device. Now it's sitting upside down. This is the suction side here. This is the pressure side. It's 10 feet into the page. The guy in the white he's big. He was tall. He was like 6'6". Okay. So it's not a tiny device. Notice it's quite shiny. These are just the remaining tool marks that you can see there. And this big square thing here is the tang. So to put it in the water tunnel, you got to hold on to it. So we had it's like 20 inches long and 7 inches in diameter. There was enough metal there to hang on to, so it worked quite well. One thing I can tell you, sitting here, that trailing edge and the leading edge, you look along the edge, is perfectly straight. For some of the tests that we do, you could see the whole thing. As you looked in the water, so you can see the whole thing arcing. So at the highest flow speeds on the water tunnel, we were up north of 130,000 pounds of lift. Okay, in the test facility, this is the U.S. Navy's William B. Morgan Large Cavitation Channel in Memphis, Tennessee.
How long did it take to make?
It wasn't that long. This is what these people do. For them, though, it was weird because of the two-dimensional shape instead of this big spiraling thing. So by the time they did the casting and then the machining and then the polishing, it was on the order of months.
Months.
Yeah, not years. Not like the current project. So the LCC, the test section is here. The test section is this size. It's about slightly more than 40 feet long, and it's a 10 by 10 with a sort of like stop signs, and the corners have cutouts. So that's where we mounted the foil. This is, as it's been described, this is the inside-out ship. The water's on the inside, the air's on the outside, instead of the other way around. And these are people, so it's a water tunnel, but it's the size of a large wind tunnel. And it was Phil Yarnell, who was one of the managers, said the energy flux through the test section is about the same as the energy flux off the surface of the sun at high speed. So here's the foil mounted in the test section. So side to side and top to bottom, this is 3 meters. Obviously, you're looking at the leading edge. Now you're for me to take this picture, I'm in the water tunnel, and I can only back up so far, and then I fall into the contraption. So that's as far back as I could get. This is the manhole, and this is the ladder that you climb to get out of the test section before the test starts. And this is not a flaw on the surface. That's the reflection of the manhole opening. So it was just a fun test to look at. Okay? That's installed in the test section. And then the tangs are buried in that wall and in this wall. And anybody know what the most difficult thing about the test was? In terms of getting the experiment to run correctly? Any guesses? Okay, so based on the shape and based on the orientation, pressures on the top and bottom of this thing are really, really different. So there's all kinds of water wants to shoot that gap at the end. Gasketing on the sides of the foil was one of our biggest problems. Because anything you put in there, boom, it get chucked out, stop the test, go in, find something else, put it back in place. But anyway, that was just an oddity.
So how many tries did it take before you got everything to just like stay in place?
We're not
and
going
get
to talk
successful?
about it. We had a very ambitious test plan going in, and we completed a third of it.
Okay.
So anyway, so here's some of the features. The flow comes in. We actually operated at zero angle of attack with respect to the flat side. We develop a suction side boundary layer, a pressure side boundary layer. Those come together, and then we create a near wake, which is where all the action occurs. There's a window here, in which we did particle imaging velocimetry, essentially one joule per pulse laser, so 800 millijoules. So it was one of those things where Josh Hamill and Carolyn Judge and me and Steve Sessio had we all are still, our vision's all still good, so we followed the rules. Anyway, so in the near wake, what you'll see is the suction side, or the pressure side and the suction side, little region of reverse flow in this parameter YF. It's Navy notation, not mine. Is the distance between the peaks of the Reynolds shear stress. So the boundary layer on the top is effectively vorticities the other way from the boundary layer on the bottom. So the bottom one is sharper, it's not diffused. The top one, it is diffused, but you can still define the peak, and we could get that out of our data. And then the vortex shutting and the features in the near wake. So here's the measurements made: upstream inflow, leading edge column, and then it's called Viosense. There's a company out there, Darius Madaris, and his wife are still running it.
MSC.
Oh, is that MSC?
I think it is
Is it? Okay. Anyway, one of their first installations of a little traversing LDV was used here. So we got this really interesting boundary layer column right in the middle, because we could, the foil stick, it's 7 inches thick. We just had the machinist cut out of the middle of the foil. There's so much metal there, you can put a big hole in the middle, it doesn't change the strength. So we could drop one of these in, so we could get a near mid-chord boundary layer profile. And the main measurements were made here in the near wake, and then of course we had a far wake column. And we had enough information, we could do lift and drag with control volume calculation. Also instrumentation on the foil. The red and the blue are pressure taps. We then have dynamic pressure sensors here at the back. And here's the onboard LDV. We had a few accelerometers in place, because if the whole thing starts shaking, we've got to shut the test down, because you don't want to be in the newspaper the next day for bozos from the University of Michigan ruined the Navy's largest water tunnel, has expensive model, breaks free and crushes downstream, all the stuff downstream of the test section. So we were able to monitor it all good. I'm here to talk about it. The foil's still all good. The
Sorry, can you go back to the previous? So you also had, you were making measurements near the leading edge, pressure measurements.
Yeah.
Leading edge also. And all in all.
You'll see those. I'll show those just a minute. So we shined the laser down from the top and then looked with cameras from the side. So the visualization box was about this big to look for vortex shedding. What you'll note then is, and so things I show you, there's no data forward of the leading edge with the PIV, because it didn't show. So I don't have PIV results on the pressure side forward of the leading edge, but I do. So flow speeds, we ran from 0.5 meter a second up to 18.3, which is the limit of the tunnel. And that got us Reynolds numbers between 1.4 million and 60 million based on the chord. So what we learned is that at speeds up to about 3 or 4 meters a second, the water in the tunnel uses all the stiffeners on the tunnel as cooling fins, and the water temperature will go down. As you get higher in speed, then eventually now you're heating the water. So we had to alternate tests to keep the water temperature from getting out of control. But in the end, we were able to get to quite high Reynolds numbers because we both had hot water and a large device.
Did you know that going in, or was that?
No, we found it out.
You found it?
Because you're trying to monitor everything you can. And you know that if you're dumping 10 megawatts of power, even though it's a lot of water, you know it's going to heat up. Okay, so then we had the capacity to do 3 angles of attack. As I said, we got through 1/3 of the test plans. We just did 0. 2 trailing edges. We had the baseline, the thinner one, the modified. And then I tried to do a tripping study, figured out that we did not know how to do tripping on a curved nose of the model, so we gave up. So all the experiments I show you are untripped. Experimental results. So here's the pressure coefficient. So this is downstream distance. The model is right here. These are measured on the sidewall. These are measured on the sidewall. This loopy thing in the middle is the static pressure measurements from the model itself. I'll note that I've got minus the coefficient of pressure. So the suction side, pressures go up because of the minus sign. And then the pressure side, they come down. And you can see I've got just a little variation between high and low, the high and low Reynolds numbers. So from this point of view, the performance of this thing isn't really changing from a lift and drag point of view. You know, because, oh yeah, there's some little changes down here, the trailing edge, and there's some differences here, okay, right in the, right at the leading edge. So here, a typical Reynolds number scale can work for you. These are then the suction side boundary layer profiles from that little LDV. Now, these are straight up average measurements. So you would never actually record one of these profiles because they typically would be a combination of turbulent profiles and lambda profiles. So the low speed stuff is over here. And this is, if you compare this, remember it's on a curved surface. If you compare this to the Blasius profile, kind of close. So this is at the lowest speed, and we're pretty sure that the flow is laminar at the midpoint. Then as you increase the speed, you eventually get to this one that's the dots, and it comes down and crashes rather cleanly. And that looks a lot like a completely turbulent profile. So we were able to pick that off. As the flow speed was going up and the location of transition was moving towards the front of the foil. And by a sense.
So 8 million seems really high. So that's really impressive in terms of very low free stream disturbances in the sky.
Right.
That you got.
Up to this point, flow is accelerating.
So it's the acceleration.
It's the acceleration that's helping you too. Yeah. The LCC is like, I think the nominal number is around the percentage fluctuation level is like 0.2. There's one flow speed where it goes up to 0.3 for the most
The
part.
foil is really smooth.
Yeah. You said we polished it.
That's impressive.
This is chord-based Reynolds.
Yeah.
RDC.
Well, yeah, these are chord-based Reynolds numbers. So at this chord, it's only 3 million REX when you get there. So, but it's still, because the flow is accelerating, it's staying on there.
That's keeping.
Yeah. So then here's some of Dwayne's PIV measurements. This is now the average stuff. So this is vertical distance. This is streamwise distance right here. This is the trailing edge. This is with the modification in place, and you can see we do have a section of reverse flow. So this is this might be, as you expect, the pressure side boundary layer comes off. It's very thin. The suction side boundary layer comes off. You can see it's much thicker because it's being diffused as the surface pulls away from the flow direction. There's some of the geometry and mean flow effects. So here, not only in the same condition, so this is the baselines in the black, the modifieds in the red. And by adding that, adding 15 pounds to 14,000, you can make the boundary, you can make the weight a little thicker. Okay, now here's the first clue that something interesting is going to be going on. The second one, this is now all for the modified trailing edge. The lowest Reynolds number is the black. Then as you go up in Reynolds number, it gets a little thinner. Then it goes back and gets thick again. And you get this because you're getting laminar flow up to a certain point, then it transitions and you get turbulent flow. And the development rate of these two things are different. So in this case, this is what was going on. We wound up with this, those curves are not monotonic.
I'm sorry, Dave, can you say that again? Initially, you get laminar flow.
Yeah, this one, the black one is the lowest speed. Now I go up in speed and it gets thinner.
Yeah.
And then I keep going up in speed and it gets thicker.
Right, and your reason was?
Was the amount of laminar and turbulent flow changes. Plus, you got to add in the curvature effect. Because I mean, as everybody knows that laminar boundary layers are pathetic when it comes to staying intact. So as soon as you have any adverse pressure rating, poof, it just pops off the surface. However, the turbulent boundary layer will stay attached, but if it's not that turbulent, it'll get thicker and thicker and thicker. And that's what, I think that's the kind of thing that's going on here. Okay. So then, here's then compilation of some PIV. This is the same sort of thing. One is the trailing edge, and this is downstream. This is upstream. Note I don't have any PIV measurements here because I'm in the shadow. And we've got results for, this is the second Reynolds stress, the variance of the vertical fluctuations. And you notice that black curves are 1.4 million. And at 4 million, you get this interesting feature. The amount of red here goes way up. This turns out to be the vortex shedding condition. Okay? And you can see it now here just even in the statistics. And by the time you get down here, it's not that different. But here, there's an enormous thing when the flow's coming off the bottom. It's really going on. So this, the pressure coefficient was okay with Reynolds number scaling. This ain't gonna work. You gotta have another way to scale this flow. There we go. So now here's some instantaneous PIV images. So, things to point out, this is the tip of the trailing edge. This is the location of my furthest aft pressure transducer. You physically can't cut any more metal away and still put the thing in. So that's as far aft as we could go, and that's at 99% coordinate. There's LDV measurements were made here and here, and then here and here. And then this is an instantaneous vorticity based on measurements that Dwayne made. We actually had a field of view here and a field of view here, and I think Dwayne patched these together. You can see there's some structure here, sort of orange, blue, orange, blue, orange, blue. And this is at around chord-based Reynolds number 4 million, but this is the baseline trailing edge. This is not the naughty one. Here's the same thing, and I just put that long sliver of metal on the back of the foil. Now it's orange, blue, orange, blue. It's quite a bit strong. This is the vortex shedding condition. So this is what we wanted to. This is what we want to. If I now go up in speed, yes.
So the non-monotonic change in the wake thickness that you saw, did it exist in the baseline case as well?
Not as strongly. For the purposes of the seminar, we show the stuff where it's a little more obvious, but we had some of the same features. Okay, it's just the it turns out that as the boundary layers leave the surface on the suction side and the tip of the foil on the pressure side, the more symmetrical that flow is, the more it's like the stupid cylinder and it wants to oscillate. This is a case where the boundary layer on the top is way thicker because it's been turbulent since the front. Okay, and so it's turbulent all the way up to the midcord, and then it's diffused all the way down to the suction side. So it's enormous. And this is now the hissing, whooshing sound that is really not very special at all. So now here's some spectra taken at those measurements. I believe it's from the LDV.
So Dave, this is not, this is fairly quiet. It's not noisy because the boundary layers are turbulent.
This would be okay from, let's say, a quietness point of view.
It would be.
Yeah.
Interesting. Because it looks like this also has some coherence, but it's in.
There's some, but it's a lot less.
Less.
It's a lot
And
less.
it's the turbulence in the boundary layers. Yes.
That launches it, but then it's the near wake. It's the Vortex organization that winds up giving you the,
So it doesn't.
yeah. So here's some spectra. This is from the baseline trailing edge. So this is frequency scaled by the anticipated shedding frequency. So Fs here is the anticipated shedding frequency. This is the measured frequency. And for the purpose of acoustics, this is effectively decibels relative to the free stream dynamic pressure. And you can see that a lot of the curves are down here, but the one that pokes up the furthest for the baseline is 1.5 meters per second, and that gets you to Reynolds number 4 million. There is also you're up a little bit at 3, and you're up a little bit at 1, but this is the naughty one. When you go to the modified spectra, you see how the blue jumps way up. Okay, so by going to the modified trailing edge, we pick up a lot more fluctuations, and because of the scaling, these are occurring at the shedding frequency you expect based on the amount of bluntness.
Is that scaling intuitive? The distance between the peaks of the shear stress and that gives, it
Okay.
nails the,
Okay, it is. We were the benefits of decades of this stuff going on in the Navy. So they told us, use this, use this, use this, because then when we made our plots, which are in the open domain, they can take our plots and they can open their folders with the real stuff in it. They go, oh, that's this was to help. So they could translate their stuff easily to the tests that they actually cared about for the hardware.
So the YF is it kind of like a VC lens?
It's the distance between the peaks of Reynolds strip curve. So it's sort of like a wake thickness. So we're the beneficiaries of people having figured a lot of this out. So that's not my discovered scaling. Okay, that's me and Dwayne and Steve got that data.
so there's a paper, there's something there that resulted in that, because that's pretty impressive. Is that Bill Blake?
Yeah.
Work?
This Bill Blake Jones stuff.
So the YF here, that's like an assumed distance, and then you could recalibrate it after you actually had the LDV measurements if you
Yes.
wanted to? Okay.
Yes, we could, but you gotta remember that, I'm working with the Navy. They handed me the shape. They had already done wind
Got
tunnel
it.
tests with
Okay.
this shape. Now we're doing a water tunnel test. They could say, you should expect this to be 1%.
Okay.
And so we said, okay, we're gonna go with that number, and we just made it 1% all the time.
Okay.
And it still worked really well. So then, now I go to that one pressure transducer, which is about here, at the trailing edge. And now I can do the same thing with pressure fluctuation. And this is with the baseline trailing edge. And right here at 10 to the 0, even at all those different flow speeds, got nothing. Now, I put on that extra piece of metal and make the edge slightly thicker. And look at this, 1.5. It should be down here. It jumps up by almost 20 decibels. That's the condition. If you want to stay hidden, that's the condition you want to avoid. Because that now is exactly what I showed as a cartoon. That's the trombone. That's the trombone when you want it to sound just like a bunch of 3-year-olds all doing percussion.
If you, can you go back to the previous, it looked like the baseline had a peak at higher frequencies. Yeah,
Yes.
the red one, yeah.
Yes. Okay.
What is?
There's some things that you don't ever fully understand. It's a big experiment. You can't go back and finish everything. That could easily be electromagnetic interference from something else. Okay. I could go in and find it out, but it didn't reoccur, so we decided, we gotta show it, because we measured it, but we didn't take it out.
Just curious.
Yes,
Also curious about the shape of the spectrum, the broadband shape. Like, is there any model that can predict this, like, fall-off shape?
there's correlation with prior measurements,
I see.
and there's CFD. See, with CFD, you could get the shape. There is a anomaly, there should be a power law into this region, I think it's -1/3 or something. But, because we were working with flows that had curved surfaces, we didn't try any of the flat plate or ordinary flow scalings. So we're comparing against our own. The fact that essentially you could say the background noise level is what's pushing this up. Because at 1 meter per second, I'm dividing by something small, so any flaws I have in the data get elevated. Whereas at the higher speeds, I'm now dividing by a big enough number that all the jumpy stuff is pulled down. Anyway, so we got the peak. So now, can we figure out how these things go together? This is one of the reasons Dwayne graduated. So the primary observations, trailing edge geometry influences the vortex shedding, it sets the initial distance between the separate boundary layers. The Reynolds number then determines the boundary layer profiles at the trailing edge, because particularly on the top, transition is 1. So the question is, how are the average and fluctuating flows coupled, and what is the parameter that determines this coupling? So Dwayne tried a number of things. We had essentially pressure measurements, and then he went to what was available at the time, some of the integral based, sort of like Thwaites method type stuff for turbulent flows, and was able. Actually, this was the first thing was for transition. He just used the simple method of Mitchell, and was able to predict where the transition occurred. And this nominally matched what we got from the LDV, which was here. I showed you. He also then did these are the suction side calculations of the boundary layer thickness. This actually came out pretty well. And here's for the separated boundary layer thickness right near the trailing edge. Not quite as good. And these are interesting. Here's the trailing edge. This is the locus of maximum vertical fluctuations. And then these are the values of the maximum vertical fluctuations. And you can see that at Reynolds number 4 million, it's not in an unusual spot. But you do get a nice high peak in vertical fluctuations in the trailing edge. So there's something going on, which makes Reynolds number, chord-based Reynolds number 4 million, a lot different than the others. Similarly, this is another one. This is the based on the parameters that he measured. This normalized power spectrum of the vertical fluctuation component, 50, 17, 4, and 1.4. You can see this the fluctuations are out of control. So 4 million is this. So this is now suggesting that there's vortices in this wake. And the question is, how do we find vortices? Okay, are all of these true vortices? Does anybody know what this one is?
Is that Saturn?
Somebody? No, when I gave this talk in Georgia, they got it.
What about vortex?
Katrina? It's Rita. This one went over Atlanta and people are not happy. So that's a hurricane. Okay. This one is like the spiral nebula galaxy or something. So this one is a vortex, but it's driven by different things. This one is driven by gravity. This, of course, is a coffee cake. This is a water wave. And one of the ways to describe water waves is with surface vorticity. So you could claim that this was a vortex. Anybody have an idea what that one is?
That's like the top of someone's head.
This is the top of my youngest son's head. He was like 6 months old. So one of the ways to determine a vortex is to look for vorticity. Now, if you had a very, very clean shear layer, you'd get a line. Okay? But if you had a series of vortices which supported the same velocity difference, you might get a series of dots. So Ron Adrian and some students, like 25 years ago, figured out that if you want to look for discrete vortices, you actually want to interrogate the swirling strength and not just the vorticity. So these are two images from Dueno's stuff. This is the vorticity, and you can see that there's some difference. And see this long thing here. This is effectively a little piece of shear layer. There's just really one vortex in it. And out here, it's actually for this effective swirling strength. It's an agglomeration of vortices which are partially canceling each other out. So I'm going to show you swirling strength. This is computed the ordinary way. This is like the imaginary part of the binding values of the two-dimensional velocity gradient tensor. We're not going to go into the details here, but it's a way to pick out things that not only have flow like this, but also flow like this at the same time. Yes?
Does that work for three-dimensional velocity fields as well? Or?
As far as I know, a three-dimensional vortex would have to have a two-dimensional slice. There has to be a way to slice it to get it in 2 dimensions. So if you can slice it the right way, it will apply. So if you're doing a great big calculation and there's vortices in there, if you can find that vortex tangent direction and look in the plane perpendicular to that, you can use this. So here's instantaneous fields at, this is with the modified trailing edge. So this is at 1.4 million, 4 million, 17 million, and 50 million. This was not that instructive, okay? So I've got this swirling strength. It's sort of, you can see 4 blues on the bottom, maybe 3 sets of red on the top. Here's 3 sets of red, 4 blue. Now this one might have a little bit more structure. This one seems unstructured, and this one doesn't seem to have very much structure at all. So we did something that was very standard in those days. Do essentially an average where you pin, you pin a vortex at one spot, and then you always look at the fields around it. So what we did is we went to this vortex, this spot, and we looked for something that obviously had come off of the pressure side. So if there's a blue dot in all 4 of these, okay, this conditional averaging ensures that we always have a vortex there. Now at 1.4 million, I got red stuff, and then it's kind of diffuse. This one, red, blue, red, blue, red, blue. This one's the blue stuff, some orange stuff. Again, this was the structured field. So now we can say with some confidence that when we do the conditional averaging, okay, you see the vortices in the positions you expect, and you wind up with the vortex shedding. Then Dwayne said, okay, I'm going to take, okay, I've got to finish up quickly, so we'll skip over this. So Dwayne said, I'm going to take this thing, and I'm going to try to make a geometrical scaling law. And the scaling parameter that came out is essentially a vertical shear rate divided by the free stream speed divided by that distance between the peaks of the Reynolds shear stress. So this is a dimensionless number. And he's able to get that from his instantaneous velocity profiles. And then he went to the spectra and said, I'm going to find a peak. I'm just going to draw a straight line across the bottom, and then look at the vertical distance. Now again, we're not the first people to do this. We came up with the shear shedding parameter, but the Navy people had already said they were already using this spectral difference as determining the strength of vortex peaks. And then he plotted it. So here's that dimensionless mean shear rate. And then here is that normalized peak height. And then Dwayne's stuff is the red and the green. And the blue is from Bill Blake from like 15 years earlier in a wind tunnel. And within turbulent state, it all fit together really well, and Dwayne was on the way to graduation. So we got all the way to the end, we got it scaled, and then this, if you can predict this now with your CFD, now you're in a position to say when you're going to get vortex shedding. So, summary and conclusions. We now know a lot about this, okay? It has to do a lot with the boundary layer development. the initial wake geometry, and then whether you're the right distance apart and how symmetric you are. And eventually that should give you vortex strength. So the final thing, you were able to do a unique set of high Reynolds number experiments, 2 GFM papers. These results extended the understanding of vortex shedding from two-dimensional surfaces. And the correlation between shedding strength and the mean suction side shear rate provides a mean to predict the existence of vortex shedding if your mean flow calculations can get the mean flow properties correct. It's a big if, but if you can do it, you do it. So that's what I've got. The next thing is questions. Thank you.
Very nice, thank you. About 5 minutes of questions.
Yes.
In the final chart, the thing goes up to infinity.
Okay. This is entirely scaling based on experimental data. That is the fit line that Dwayne chose to put on there so that it would look good. So there's no theoretical fit there. The idea is just to show that the broad sweep of the data allows the prior measurements and the current measurements to fit together, even though they're made in very different conditions, different facilities. So if you keep heading in this direction, I presume it goes up higher, but eventually at some point you saturate. Eventually all the energy in the flow now is bang, 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 and all these vortices, and you can't go any higher.
What it suggests actually, the x-axis is interesting. It's like there is a bound on the value of du dy versus u naught by yf that you can get. That's like 1.6, 1.7, isn't it?
Yeah, we get farther and farther.
That's what it suggests.
Yeah.
And it's like you said, ultimately if it goes into this, that's probably an upper limit. How are you, in what form are you putting your shear stress? Your stress there, right?
Yeah.
That's what the x-axis is, which is, I didn't do that. That's very good.
Is this scaling, can you do this for just regular wakes too? Meaning partial U, mean partial Y.
You probably could, but we didn't ever try that.
I was just thinking.
This was set up precisely because we knew we had pressure side boundary layer and a suction side boundary layer. And all the interesting stuff was going on the suction side. So you notice there's no pressure side part of this.
Because in a wake, the partial U bar versus Y profile, you can have a deficit, right?
Yeah.
And then, maybe you can try something like that. I don't know how to go read some literature, but this basically what you're saying is that it's that mean shear rate divided by the mixing length times the free rate at which things are moving.
What that parameter has is, you could get the same shear stress as just U1, U2, and it's a gradient. But you could also get it as the average of vortices that are shedding.
Yeah.
And it's comparing the two in some sense, and that's why there is a bound, right? That's why it shows a difference.
So is the U naught over YF kind of like a proxy for your Stru-Hall frequency? It is, right? Like
This is a the shear rate.
right. That yeah.
This is a scaling parameter, which essentially is telling you how fast the flow is moving and how big the wake is.
Wait, that's the 3 units of 1 over time.
Yeah.
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 That's really good actually.
How much of this that extent is needed?
How much what?
How much of the findings would apply to in three-dimensional, like with twist and curvature?
Oh, wow, that's a good question. I really don't know because this whole study was intended to be as near to 2D as possible. So I can make guesses.
You said that in this experiment only did 1/3 of what you wanted to do.
Yeah.
What would you like to do?
The next thing was to actually try this at positive and negative angles of attack. Because as you go to a positive angle of attack, you could make this even worse. You could diffuse the upper boundary layer even further. If you went to negative angles of attack, maybe you get the two separated boundary layers matching even better more over time. You might actually pick up more vortex shedding.
We should probably follow up on that because hydrofoil is going back in and Danny wants to do measurements downstream. And we could, you have the room?
In 2 minutes.
2 minutes, yeah. So Danny, we should talk about this. Thank you again.
How long did it take you to find your slides from 20 years ago?
I've been doing this talk about once every 5 years.
Oh, really?
Yeah.
It keeps, it stayed
The
relevant.
biggest problem is they update PowerPoint in between.
Right,
They're
right.
gonna find a way to make it work again.
Yeah. All of a sudden, all the text boxes are in different places.
Exactly. Yeah,
The fonts aren't supported.
you've been